morning, and thank you for joining us, and welcome back if you were at our last presentation. We again are coming to you from California. We are Heron Innovators. This is our virtual booth for WEF-TEC 2020. Please bear with us as we did have a few technical difficulties at the start of the last session. So again, I just want to check if you guys have that chat feature. If you could please chat in there, let me know that you can hear us and see us and that everything's good, and then we will dive right into our presentation. For now, I'm going to go ahead and introduce myself. Again, this is Heron Innovators. My name is Andrea Hofstetter. I am joined today with the president of our company, John Barsotti, and remotely we have joining us from Kentucky is Jeff Knolenberg. Unfortunately, he couldn't be here in the offices in California. He is quarantined due to COVID. But for now, I'm going to go ahead and let John introduce himself. Again, this is Heron Innovators. We're home of the SAF, and then I'm going to pass it on to you.
Thanks again, Andrew. My name is John Barsotti. I'm the president and founder of Heron Innovators. Again, we have I just want to really thank you for joining us and hope that you and your families are safe in this time of COVID. I know all of us are in kind of a awkward working situation. Most of us working from home. Not all that much availability at our customers. So, and this is, I don't know, Andrew didn't mention it this time, but she certainly mentioned it last time, and I'm going to mention it. This is very unusual for us. We're much better at talking to you face to face, getting our cues, getting your questions. So we're going to miss something. There's a chat feature. Please use the chat feature. We're likely to miss something, and even our conversations between us just before this, we could see that we're skipping around things wrong. You know, we're not professional presenters in this regard. All right, I'm gonna turn this over to Jeff. Jeff's gonna introduce himself, and then he's gonna talk a little bit about biosolids thickening primarily. Jeff, you're on.
Thank you, John. Andrea. So, greetings from Kentucky. Yes, we did have COVID in our household, so I had to quarantine. But glad to be here. I'm glad that technology has allowed this. And anyway, our topic this morning is breaking the paradigm of solids thickening, particularly in an industrial setting. And of course, I guess we first have to define what is that paradigm for solids thickening. And I thought I might just take a few minutes and talk about what thickening is. And first off, what are those solids? So typically in wastewater plants, industrial wastewater plants, you've got a primary stream, which is the raw water coming directly out of the plant, and that generally goes through some kind of pre-filter or pre-treatment technology. Very typical is a flotation technology, of course, which our technology, SAF, is one of those technologies that's available. And so there's usually screens or some type of or some type of flotation technology, and then either it goes on to a POTW or some kind of discharge, or it may go to secondary treatment that the plant may have, where we've got biological processes. And of course, those processes are creating solids. And there's two that we typically deal with, one being aerobic, the other anaerobic solids. And we're going to hit on all three of those: primary, aerobic, and anaerobic, the two subcategories in secondary or biological solids. So typically what's done, what I think we see most of the time for primary, other than, I think people rely on their flotation to do thickening for the most part. Occasionally you run across where people have additional thickening technologies or dewatering technologies. But secondary, of course, we see that even more so. And so let's define what's the difference between thickening, dewatering, and then there's even drying that's sometimes used. And that's probably more in a municipal setting is probably where we see dryers. But as far as thickening, and John, feel free to jump in here, but I think mostly what I see is gravity decanters, or we could see GBTs, RDTs, screw presses. A screw press would be getting more into what we would consider dewatering. So you've got thickening, which is taking the solids up to a certain level, and that's again, can be a gravity belt thickener, or rotary drum thickener, or even just plain old gravity decanning. But and then you've got a dewatering step, which typically encompasses more like belt presses, screw presses, the old style. There's still a lot of the presses that are used out there that are manual, the chamber presses, filter presses. And then, of course, you can move up probably what you would be considered top of the line, although it's got its pros and cons, would be centrifuges. And that's the world I came from, was the centrifuge world. And which is where I first got involved with this SAF. That's where I first heard about it. I was working for a company that built centrifuge systems, and I was trying to figure out how to better break the emulsions coming off of traditional flotation, in other words, DAF, dissolved air flotation, how to better break those emulsions with a centrifuge. And we're going to get a little bit more into that. John, I just want to check, do you have anything to add about what solids thickening? Any other comments about that?
Well, I'm not sure I heard it right, so I'm going to just say it. But so we are considered part of that step in thickening, right? The SAF is so to be dissolved there. If you would, you've heard of DAFT. This would be SAFT, right? Right? Suspended air flotation thickening. I'll turn it back over to you, Jeff. That was all. I didn't quite hear if I heard that or not. Yeah.
Excellent point. So I'm going to pull up some slides. Let me know when you can see these slides.
We see them here, Jeff. We see it. Yep.
Okay, great. So as I said, I was involved with centrifuges used for dewatering of solids coming off of DAFs. I was working primarily in the food industry at that time, and had some background with the ethanol industry as well, doing exactly the same thing. It was thickening solids or dewatering solids coming out of an ethanol plant. And then I transitioned to food plants, and as I said, there's an emulsion, and that emulsion is created for several different forces, I guess. One of those would be chemistry. Polymer that's often used creates an emulsion, and then we're trying to mechanically split that polymer or that emulsion with some type of mechanical force. Of course, with centrifuge, we're using centrifugal force to do that. And I was walking a trade show, and I think it was fact in talking with a chemical vendor. That fellow mentioned SAF to me. And he said, you can get by with less polymer with SAF. And that piqued my interest. I thought I ought to check into it. He gave me John's number. I gave him a call. This was all 3-4 years before I went to work for Heron. And in fact, I called up John, and we started talking about this SAF technology, which I had never heard of before. But John met me in Arkansas and at one of my clients. And what you see in front of you is a jar test that we did in their lab. We had gone around throughout that morning and had grabbed samples from various points in a number of their plants. This particular jar has water that had gone septic. It had sat in a wet well for several days. The pump was down. This was some pretty nasty water. It stunk. And so what you see, and I'm going to start this video here in a second, but you see we've got a pin flock formed. There was a little bit of coagulant, a little bit of polymer. The coagulant breaks those solids out of solution. Polymer helped bring them together, but maybe a half a ppm or 1 ppm of polymer. And this tube right here is coming from John's SAF lab unit. So we're about to inject in a charged microbubble froth, which is unique to SAF. So let me start this. And I think what you see is those particles are actually getting bigger as the air attaches, and what we're getting is a very high capture rate, a very fast rise rate, and a very stable float. All three of which was something that I had never seen before. In fact, the environmental manager from this company, he said, "Wow," when we saw this, and So I went along with him, and we visited 3 different installations, SAF installations across, in 3 different states, in fact. We ultimately ended up back in California, and we're going to talk about that application in a little bit more detail. But first, let's talk about SAF, and actually, what is SAF? So let's start off by talking, to contrast with SAF, or to explain SAF, let's contrast it with the traditional technology, which would be dissolved air flotation. And I know, John, a lot of times we like to use the slogan, flotation without dissolved air. So the question is, how do we do that? And so what we're showing in this diagram is a flotation vessel. So you've got influent coming into this tank. This could be a rectangular. There's also round tanks out there that are DAFs. And the way most of them work is you've got a recirculation stream going on here where you've got a recirc pump, you've got, and that's pushing against back pressure, and you've got air being injected into that. So at pressure, air dissolves in water. And how much, in fact, what we're going to do is dissolve that air up to the saturation point. How much is dependent on laws of physics. It's going to depend on temperature, pressure, and as well as the conditions of the water as far as how dirty that water is. So how much, where that saturation point is determined by all those conditions, but when that water then re-enters the flotation vessel, you're now at a lower pressure, so you've exceeded saturation, so little bitty soda pop bubbles are going to come out of solution, and they're going to work to float the flocculated solids. They're actually going to lift those solids from underneath, be floated and skimmed off and disposed of, and then the thickening process. Or actually, we're going to come off of this at a certain thickness. And what we'll talk about a little bit more is, what do we typically see with the DAF? What do we see with SAF? So let's talk about SAF. So as I said, what SAF is flotation without dissolved air. So what we're going to do instead is create a charged microbubble froth that with a froth generator. So it's a little skid. It's about 4 by 4, 4 by 6 foot in footprint, and it's going to make charged microbubbles. This froth that is 40% air by volume. And I'm going to ask John to explain a bit what these bubbles are. A lot of times we're saying, well, you're just getting more air into the system. Well, John, elaborate on that. What's different about these bubbles compared to traditional flotation bubbles?
Yeah, our bubbles are covered in a surfactant sheath that are 7 to 25 microns in diameter. And that sheath, that surfactant, is both, gives us surface tension advantages and it gives us charge advantages. It's electrostatically attracted to the particle. So we overcome the surface tension issues of the particle, and then with that charge advantage, we see about 1,000 times the affinity for attaching to a particle in solution. Given that our air doesn't coalesce readily, right? It takes a few minutes. A lot of our air is used. It's received better. We get a lot more air on the particles, and with that we get not only just the charge kind of helps us in the size of the particle, gives us kind of a coagulation effect, which allows significant reduction in treatment chemistry, as well as a really fast rise rate because so much air gets on the particle. Jeff?
Yeah. So those bubbles then, that charged microbubble froth is injected here. So 40% air by volume instead of 2 to 4% air that you normally see here with the DAF. Is that right, John?
It's about right. Yeah. Saturated is usually 2 to 5%. Actually, used air is more like 2%. So a lot of coalescing goes on, right?
So then the froth is injected here, and it's actually. So if the influence coming here, the froth is injected here where it's stirred in, and of course this is what we call a clear floater mixer. I'm sorry, a clear mixer actually. We've got the clear floater for the flotation cell, and then the clear mixer. So these paddles are turning. This shaft is turning about 10-15 RPM. That's driven with a motor at variable speed. So we're gonna just stir those bubbles in to get a good air to particle reaction. So those bubbles are going to be attracted to, because of the electrostatic attraction, they're going to be attracted, they're going to attach, and they're going to encapsulate the solids just prior to going into the flotation cell. So that all happens right here, and then we go into the flotation cell. So, and we've got a lot of ground to cover. We've gone through SAF here real quickly. If you've got any questions on that, please feel free to type that in the chat. And but let's move on. So John, let's talk about actual installations and solids thickening. But first, what are these components that we're looking at on the screen?
Yeah, so on the top left, you see what we call our clear mixer, which is that paddle mixer that Jeff was talking about. And you can see it actually on the side of the clear floater, which is our version, the Heron version of a float cell. What's unique about our float cell courses, and I'll get into that a little bit, is that we flow across the cell so that that mixture actually covers the entire length. It has 2 injection ports, and that introduces processed water over the entire length of the clear floater. The slide to the right is a SAF generator, what we call our SAF generator, which is really the secret sauce. It is our proprietary patented or patent pending design. It generates an AFRON, the literature calls an AFRON. What we've been able to do is figure out how to scale that, and those are and it's all done in these SAF generators. And one of the beauty of our SAF generator is that by the turn of a diaphragm valve, I can provide more or less air, flotation air, to the process. On the bottom is a traditional flock tube that you see on most DAFs. We don't use it except really for the purposes of coagulation, where you need some residence time, or pH control, where you might need some residence time. Otherwise, we feed polymer. Oftentimes we feed polymer, not always, but oftentimes. And when we do that, that gives us the ability to distribute it in a few different places. I would say nearly every one of our installations, we're feeding all the polymer within the last 10 feet of that flock tube. And on the right side is one of our clear floaters that actually in Arkansas, and that's a CF1000. And what's unique about our clear floater is that we do a cross flow approach, so that we feed all the water along the length of the unit, and the pickup weir is on the entire length of the far side. By doing that, we slow the water down and we achieve those really high hydraulic loading rates that we are accustomed to, and that's 20 gallons a minute per square foot. That, of course, is with significant solids too, 2,000-3,000 parts per million. The advantage of having the weir pick up on the entire length of the other side is that, for one thing, it's a very laminar flow, if you will, across the tank, and it also it's not that much affected by small changes in flow. So you're not always adjusting, or rarely adjusting, the weir. The skimming goes along the length of the tank as traditional, and it's controlled by VFD for rake speed, on and off delay timers for in situ dewatering. And we have a lot of options for bottom solids dewatering, though, because our removal efficiencies are generally so good. Most people elect to just draw the tank down once every quarter or so, once every half year, and just hose the tank out. Okay, Jeff, that covered well enough? Yeah.
Well, in fact, thank you very much.
Yeah.
In fact, what we've got in this picture on the right-hand side is, what's the flow capacity of this unit, John?
That's a CF1000. It's 140 square feet of float area, and that'll take you to about 2,800 gallons a minute in a solution that's, I think, under 5,000 parts per million. Don't quote me on that number. I have to go do the engineering on that again.
Right, but bottom line is we've had this comment a lot. Our footprint is just incredibly small compared to traditional flotation. And if this were traditional flotation, would it be a fair statement to say this would be 3-4 times the size?
Yes, I think that'd be a fair statement. Yeah.
We've got another tank right here. So that really gets into solids thickening. In fact, this particular client that we've got is doing a second decant step. So they are accomplishing, we've got solids thickening on the top, by simply controlling the rate speed. The speed, as well as putting it on a timer, we can turn it off and on. And because the solids are so stable, they'll float for hours. And so, which allows dewatering. And then another thing, in fact, John, I know that I've seen you do this, that at trade shows, where you'll actually take the solids in a jar test, put them in a beaker, seal it, shake them up, and they'll float again.
So I'll elaborate that, right? So we were at a small in situ trade show at a sewer plant where, local sewer plants came, and we did just that. We took the solids, floated them. It was in a mason jar, and we put the mason jar lid on, shook it up, refloated it immediately. The operators were so enamored by that one of them actually grabbed the bottle and started shaking it and redoing this, and I think he did it 14 or 15 times before he finally resuspended all the solids for good. So and that talks to that what Jeff's slide was just there, where we can skim off the top of our unit, get it as dry as we can off our unit, or dewater it to the degree we can. Then you can drop it into a container like that, let it sit, it will float again. And when it floats again, you'll get, another 10, 20% more dewatering. To the point where that's a poultry plant there, they're easily above 30% solids consistently.
So let's, in fact, we've got a few slides here. Are the slides still up? I want to show some pictures.
So we're looking at the conversion slide for Simmons in front of us.
Yeah, I think that's what we talk about. Now, these are mixed liquor biosolids, in other words, aerobic biosolids. This was a DAF that was actually converted to SAF. So to convert a SAF, convert a DAF to SAF, really just very simple. There's just two components. In fact, so it's the it's the mixer. So this is nothing but a drive with a shaft, paddles going through it, and I've got another picture that actually shows that right here. This is one being assembled in our shop. So you've got a drive on one end, this shaft with paddles. This is VFD controlled, influent coming in here. You've got the froth injected here. This is where we get that air to particle reaction, and then this would be attached to, this is the very last step before it goes into the flotation cell. And of course, this is turned 90 degrees. But, so back on this tank here, so coming off an existing serpentine flood flow reactor, and we custom built this, where this bolts here, this bolts to the flotation cell, and these were actually, as I said, these were mixed liquor solids. So let's talk a little bit about what kind of performance that we got on that. John, anything you want to add on this? Well, I'm going to pull up a spreadsheet while you're talking.
Yeah, so these are mixed liquor solids. They're both from a MBBR. The primary flow is from an MBBR with clarifier thickened solids fed in intermittently during the day. So we'll see, several thousand parts per million solids net coming into that float cell. That float cell was restricted. They were doing, before we got there, that was a very large float cell, and they were doing, I'm trying to recall, I don't know why I've lost this thought, but they were kind of maxing out at 4 to 5 pounds per hour per square foot on the top of that, making it very difficult to reintroduce the clarified thickened the clarifier thickened solids from another downstream plant. So in this installation, from the day they put that DAF in, they were at capacity, and always trying to deal with how to reintroduce these solids from the downstream operation while continuing to treat the solids coming from the normal MBBR. And it was, according to the client, it was a very difficult balancing act. we did the retrofit, and they haven't had capacity issues since. And while achieving, I think, Jeff, you're going to show the slides, so I won't steal your thunder. I'm gonna turn it over to you, let you go. All right. So, yeah.
I'd love to show this slide because this was what I thought was a bad experience for me. So the environmental manager from this plant was good enough to share this with me. This came from last year, and as you can see, their average mixed liquor suspended solids level was about 2,500 milligrams per liter of ppm coming in, and I think they're running up to about 5%. So this is really serving a dual role. First, we're clarifying this water, but of course, we're also thickening the solids at the same time. So they're running up to about 5%. Andy, the environmental manager, has told us he knows he can get these solids much thicker, but they're land applying these solids, which is often, we see at a lot of our plants, we see where the limiting factor isn't how thick we can get them, but where they're going after that. And since they're being land applied, that company doesn't want them any thicker than 5%. John, you got any feel for what's realistic? How thick could we get these solids?
I think aerated biomass, like we're looking at here, WAS, waste activated solids, and what might slough off of an MBVR. I think we've seen a maximum of about 10%. I'd say anything between 8 and 10% requires intensive polymer usage and real focused effort to try to dewater the solids. We easily get to 6 to 8%, and oftentimes even without a polymer we can achieve 4% in this kind of water.
Yeah, and I think it should be mentioned that after they converted this particular unit over to SAF, not only did they have higher throughput, higher solids loading, and we got thicker solids and cleaner water. If I remember right, they were running around 60 to 70% removal. As you can see in this chart, this column here, column G, is the removal that they're seeing at every single day. But the other thing was that they cut their polymer consumption, didn't they, John? Or coagulant and polymer.
Yeah, both, right? They save chemistry downstream on coagulant because the water was treated so well they could reclaim it immediately instead of having to go further downstream treatment and remove more phosphorus. And the polymer, I think they eliminated the use of anionic polymer altogether. And I think they use a lesser degree just cationic polymer. And and just if I can add one more thing, that project paid for itself in a few months, like 3 months, I think, if I remember right.
Yeah, and in fact, they ran for a while. I remember they did eliminate the anionic, but they also eventually stopped using coagulant. They're only using cationic polymer now, so it's significant. In fact, I remember it was hundreds of thousands of dollars that were saved per year in chemistry, and they cut back, and of course, we're using less energy too with this system. But let me jump back to this spreadsheet. I started to say a little bit ago, I thought this was a bad experience for me. One day when I walked in, of course, you can see they're getting consistent 99% range removal with this. And then there was a day last fall when I brought a client in to actually see this in operation. And the lab manager saw me walk in the door, and she said, "Oh, I wish you had been here this weekend." And in fact, it was a Thursday that I walked in. And she said, "Well, why? What's going on?" And she started laughing, and she said, "Well, you know that little Lovejoy coupling on your pump, which is, of course, is the coupling between the motor and the pump on our skid, that went out. They had been running for several years, and that coupling needed to be replaced. They had one on the shelf, but maintenance decided to not replace it until Monday because they said, we've got the old dissolved air system on that vessel. Let's just turn it on. Let it run and then we'll come back Monday and we'll fix it." So that was Saturday, and you can see the performance where we went from SAF back to DAF. So this is Saturday, this is Sunday, and then Monday morning they came in and 15-minute repair, replace the coupling, and we're back up and running. So it wasn't until a couple months later that I got this spreadsheet. I thought this was kind of a bad thing for me not at the time. But after I saw this, I thought, this is really the best comparison that we've got, all things remaining equal, comparing performance of SAF with DAF. And of course, as you can see, the rest of the year is good. So let me jump back to anything else you want to add on that, John, while I transition back to the slides?
No, other than we've gotten a lot of mileage out of that one project. The customer was, while you're trying to find the slide, the customer I kept, selling it to them as we can get a lot higher solids. And of course, all the engineering firms and all the chemical firms out there are in there telling them that there's no way we can do this and so on and so forth. And to the point where we were actually standing on top of this unit at one point. The customer saw that it was biomass, and he said, well, there's no way you can get between, even 7 pounds per hour per square foot on this kind of solids. He was a poultry guy. And I actually looked up to the customer and says, so what are we doing today anyway? And that particular day we were about 14 pounds per hour per square foot. And the customer almost wouldn't, it took a while to convince him that we weren't lying, nobody was lying to him. It was really what we were doing. And to the degree where we are very confident and will warranty anything, at least 20 pounds per hour per square foot. We often size as high as 30. We've seen numbers as high as 45 pounds per hour per square foot. All right, Jeff. I'll send it back to you, Jeff. Yeah.
All right, so let's come back to California. I mentioned this earlier. These were anaerobic solids. In fact, John, you probably had a lot more to do with this than what I was involved with, but this was one of the first systems I saw installed on it. What kind of flow rate can that particular unit handle?
So that's a 35 square foot bathtub on that unit. In most waters, it can handle 700 gallons a minute, about 1 million gallons a day. That entire skid with all the staging for the chemistry and all the ancillary equipment is about 28 feet long by about 10 feet wide.
So this unit, again, on anaerobic solids, talk about that a bit.
So, I don't remember the loading. That was a kind of an older project of ours, but I can't remember the loading that well. But we were achieving for a few years while they were still running that as in their treatment system. We were achieving better than 98% removal with almost no maintenance, and I think the polymer consumption was around 30 parts per million. And the solids coming at us were, again, I don't have a recollection. I want to say they were around 1%. So.
And then one more slide. And of course, we were both involved in a project not too long ago, just a couple months ago, up in Minnesota. And we were put in a parallel to another DAF unit. And we're not going to get into mentioning names, but it what we would call traditional dissolved air flotation, and they were literally set up 6-8 feet away from us. But this is our pilot unit. This is one of 2 units that we've got. And John, what kind of numbers did we see on this? Well, in fact, I remember these numbers. Let me go ahead and answer my own question.
All right.
So
Thank you.
This particular unit was, this is 17.5 square feet flotation area. And what our goal was to prove that we could load at 28 pounds per square foot, get in the 5 to 6% range on solids thickening, and do that very economically. And in fact, we've already been awarded this project, and if I understand correctly, it was simply on ease of operation that the operators all loved it, because all they had to do was come in and hit a button, and it started up. We're making good water. Another large part of the decision-making process was, of course, cost of operation. When they looked at a 20-year life cycle cost, what they saw was just considerably cheaper when you look at the cost of the amount of polymer that's needed, as well as the ease of operation. So, John, anything else you?
Yeah, I think we were remiss if we didn't mention how robust the process was compared to the competitive process, right? So it seemed like we left within a few days. We left, and the engineering firm and the operators ended up running the plant, starting and stopping it on their own, changing conditions, losing the process, bringing it back. I think the quote came back, it was at a board meeting, was something like, it's stupid easy to run, and we really try to do that. We make it very easy to operate, and it's a very robust process where our competitors, I'm not sure in the entire trial period they ever established a consistent running process. So, and that was, that gave both the municipality and the engineering firm a lot of confidence in our product. Jeff, you're on.
Yeah, is this video coming through?
Yeah. Yes, it is.
Yeah, so talk to us about what we're seeing here.
So that's actually the floated solids from that anaerobic digester. I think we're loading at most of the trial. We were at 30 pounds per hour per square foot. This is all biomass, right? 30 pounds per hour per square foot. I believe we have a few data points where we really wanted to push things, where we got above 40, like in the mid 40s. It's just not a parameter we're very sensitive on when we're doing this, which is another distinction with our competitors. You can see how thick that is. You're going to see the blade come by here in a minute. The blade's probably 6 inches, 8 inches thick, and it's completely buried in the solids. Let's see if we get that. You can see it in there, right there, right? It's completely buried in the solids, and we're still removing water at 99% removal.
Yeah, in fact, John, there was a day when I was there that we ran it closer. We were in the mid 40s.
Yeah. Pounds per hour per square.
50 pounds per square foot per hour, and still getting very clean water. In fact, I think this particular video shows what's coming over the weir. Even though, and I think we should mention, even though we're seeing a little bit of flock coming over at that time, because we were really trying to push it hard, we were still seeing around 99.5% removal. Is that right?
I think it's a fair statement. In the entire time I was there, we did things to try to disrupt the process to see, how low the polymer could go. And then, of course, we saw some substantial carryover. But when we got a stable unit, we could run it indefinitely, and we were, I think, consistently above 99% removal. The other thing is it just seems like even in most waters, that solids flux parameter, we have a lot of breathing room there. It's just not real. Our units are not very as sensitive as competitive technology to that number. Well,
I think that's it for my slides. Andrew, do we have any questions that have come in?
Yes, we do. I didn't want to interrupt anybody because you guys had a lot of really great information and a lot of really good results, and I wanted to make sure everybody got a chance to hear those. But I do have a question that came in. What is the upper limit for dewatering biosolids with SAF?
So, thank you, Andrew. Yeah, so I did answer that in the presentation, but I think it might warrant repeating, right? So you have that. In the aerobic world, it seems like 10% is probably maybe the upper end, 8%, 8 to 10% being difficult to get to, 6 to 8% being kind of a normal thickness of that biomass, and then in the anaerobic, it's kind of the same range, and then when we get in the primary solids, especially if the primary solids has some fat in it, we're looking at somewhere north of 30% solids as a pretty doable number for us.
Yeah, I've seen that in some plants, and of course it is dependent on the amount of fat.
Right, exactly, yeah.
In fact, the earlier example, which came out of a poultry plant, I know they were hitting in the 20s consistently, and we ran a test not too long ago where we actually did hit 30% solids, which That's, I think we need to qualify that did include a good amount of fat.
I think the highest level I saw in a poultry plant, I thought I'd add this, is 35%. And then obviously there's testing issues and they're all grab samples, so we get pretty high level dewateredness.
Jeff, I believe you spoke to this in your presentation, but we did get a question about can you convert existing processes? Could you maybe reiterate a little bit on the conversion process?
Yeah, and it's as John said earlier, more than half of our business probably, and how we start working with companies is usually because we're called in because the DAF is underperforming. And it may have performed very well when initially installed, but things often change in plants, conditions change, and so I can think of a number of cases where the DAF just isn't cutting the mustard, and whether that be on throughput capacity or solids removal, and so that's an opportunity for us. And so all we have to do is as I said earlier, just put in we have to find a place in the line, and that's generally not too difficult, to install that mixer so we can stir the froth. So it's the froth generator skid and the mixer. And so we're now injecting that upstream right before it comes into the flotation cell. And of course, we're going to turn off the old dissolved air system. We don't need to inject any more air to keep those solids suspended on the surface at all. So we'll see huge increases in throughput capacity as well as performance, and then we often see thicker solids too. There's all kinds of benefits.
And there's one more question that wasn't asked, and I'm gonna throw it out there because usually we get this question. Well, you're just adding another chemical, right? And so we like to see what we see normally is that the cost of in the cost of operation, the frothing agent we use to make this micro bubble is offset by the horsepower we turned off in the DAF. 7-8 cents a kilowatt hour. In your kind of normal water, we're not in the solids flux world. We're looking at breaking even there at that point. And so, basically what you spend on power, now you're spending on flock aid. So, that was it.
Okay, and I think we do actually have one more question. How compatible is SAF with other downstream dewatering processes?
Jeff, this is right up your alley here, right? I'm going to say this much. I'm going to say that in those things where there's a fabric ahead of us or a screen, the solids that are rendering is the wrong word. The solids that come off of SAF tend to be encapsulated, act like a gelatin, and release very easily. We've had many downstream, the manufacturers of many downstream dewatering devices tell us that. So your operations are easier, less polymer, and just a lot less maintenance on that downstream equipment. Jeff, you have anything to add to that?
Yeah, I can think of an application where you actually ran 3 trials, or 3 summers in a row you ran trials. And that was in California where there were 2 centrifuges. One was supposed to be redundant to the other, but the water was coming out of the plant where both centrifuges had to be run in parallel. And John, if I correct me if I misstate anything here, but I think in those 3 summers in a row, what you proved was that you could thicken the solids to the point where you could shut off one of the centrifuges and only run one. So we're cutting the amount of dewatering that needed to be done in half. And the amount of polymer that was used was 25% less in total between the SAF for thickening and the centrifuge for dewatering. So it was 25 to 30% less with the combination of the two than what it was simply just using centrifuges. Plus, with the centrifuge, there's a lot of power costs involved. They're horsepower.
We're kind of up against the clock here, so I just want to say this. So those 2 centrifuges were each 400 horsepower centrifuges, and the savings came from the operation with just the centrifuge, right? And then we were about 35% net polymer savings. We saw that polymer savings in the test, and we were put up, in one of those years, we were put up against a competing gravity belt thickener. The gravity belt thickener didn't save anything on polymer, and the filtrate from the gravity belt thickener was just far dirtier than our treated water. I want to say several hundred parts per million versus something under 50 coming off our trailer. So
I know we're almost out of time, but I also just want to mention, compared to a rotary drum thickener as well, and John, if you want to comment, feel free, but I think our polymer consumption is going to be a very small fraction.
it's going to be very less, and we just got a last second question in from, I'll let you go and read.
Yes, we have a little bit of time for another question. Does the surfactant affect the solids when they're going to be applied on soil?
Nothing. We have received no comment from any of our customers on that. I'm going to take that question, Jeff. We have received no comments from our customers, other than it dewaters more easily, it drains more easily, it dries more easily from our unit. And of course, the surfactant itself is this Valentin Garcia, if I'm pronouncing it right. The surfactant itself is non-hazardous, non-toxic, and it's actually present in very low concentrations in solution in the solids blanket. So I guess it might make things better. I've never heard anything bad about it. So I'll leave that.
John, just one more thing. I think we should point out that the surfactant is naturally occurring in wastewater.
It is.
It's already.
It's in most solid streams. It's a fairly ubiquitous compound. It's in your solid stream naturally. It's in your wastewater naturally. It is, and it's part of biomass, right? It's naturally formed in biomass. So.
All right. Well, great. Thank you guys for all the information today. Jeff, I hope you and your household fares well. And I want to thank you all again for joining us. And, if there were any technical difficulties or any glitches, we apologize. This is new, and hopefully next year we'll be back to WEFTech Live meeting you. Oh, did we get another question?
We have another question. I'd like to jump in. Valentin,
okay.
If you can still hear me, yeah, it's completely biodegradable, and you'll find it in. We've gone through anaerobic digesters with it. It's actually NSF approved for drinking water use. It's a very simple compound used at very low concentrations. Valentin, why don't you let me know that I answered your question, or if you have another question. Can you type in? Are you still on? Okay. Well, our contact information is on the screen somewhere, I would assume. So if you can email me if you have other questions.
Yeah, if you have any other questions, you can call us at any time or email us. We are happy to continue to spread the word about SAF and really inform everybody about what we do here and the benefits environmentally and to plants in general. Yeah. So thank you again, and everybody have a wonderful day.
Thanks, Andrea.